Working Package 5 of the Dycon ELC Advanced Grant is involved with the analysis of dynamical and control properties of memory and hybrid PDE ODE models. A memory-type partial differential equation is a particular kind of model which describes phenomena whose dynamics is affected not only by their current states but also by their history. In these models, the memory is introduced by a non-local term in the form of an integral in time during the time horizon of the state. The introduction of this term affects the dynamical behavior of the model. For instance, in the case of diffusive equations, as the physical process evolves, the memory accumulates and eventually injects new energy into the system, thus slowing down or even contrasting the natural propagation effects. In Working Package 5 of the Dycon project, we are particularly concerned with the analysis of the so-called controllability properties of memory and hybrid PDE ODE system. This means that we want to act on the system through some control function f located in some subdomain of the general domain in which the equation is posed, in such a way that at a given time, capital T, we have steered the state to some predetermined configuration, for instance the zero configuration, and also that we remain in that configuration for the times afterwards. In the case of a memory types equation, this means that not only the state but also the memory has to be driven to zero in time capital T, so that the system may reach a stable equilibrium. For standard PDE models, controllability may be generally achieved by acting on the system from some specific position in the physical domain. This is no longer true in the case of memory types partial differential equation. The main reason is in the fact that the presence of the memory introduces some hidden non-propagation effects in certain components of the system. This feature becomes evident when considering memory types equation as coupled ODE PDE system. From a mathematical viewpoint, this corresponds to considering a simple change of variables. We can consider the memory as a new state in our system, and in this way we obtain a coupled PDE ODE system in which we are coupling a diffusive PDE with an infinite dimensional ordinary differential equation, which can also be seen as a second diffusive equation with zero diffusion. Because of the presence of these non-diffusive components, certain states of the system present non-propagation properties. This means that they cannot reach the controller no matter where it is located in the domain we are considering. To overcome this problematic, in the Dycon team we proposed to address the controllability of memory and hybrid PDE ODE models with the employment of the so-called moving control strategy. This means nothing more that we are moving the control inside the physical domain in such a way that in a given finite time horizon it covers the entire domain and reaches all these non-propagating components. This is the same idea of a drone employed in the removal of some pollution in the air. The drone is moving in space, reaching all the particles of pollution and removing them from the environment. In this way, it is able to provide the total cleaning of that pollution. In the same spirit, the moving control strategy can ensure the controllability of memory types model. Non-propagation effects, analogous to the one of memory types PDE, can be observed in other kinds of non-local models. For instance, fractional in space partial differential equation involving the fractional Laplacian. This is another topic in which the Working Package 5 of Dycon project is involved. The fractional Laplacian is another kind of non-local operator employed in the description of phenomena which have diffuse properties weaker than the one generally described as the classical Laplacian. In this operator, the strength of the diffusion is associated to the power s. For small values of s, we will have very weak diffusion, while for s large, this diffusion will be more intense. When the diffusion is not strong enough, the corresponding model will show accumulation effects which, in the same way as memory types equation, lead to the failure of controllability properties. In this aspect, the aim of our research is to investigate the reason behind those pathological phenomena and to provide efficient remedies. Working Package 5 of the Dycon project is then committed with the study of controllability properties for different kinds of non-local equations. This is the first step toward an efficient control design capable of providing novel practical control techniques applicable in a diversified spectrum of phenomena in physical and social sciences, contributing to the development of modern technology.